Hey Phys 2 kids, Campbell here. Welcome to your first summer assignment video in thermodynamics. In this video, we're going to talk about internal energy, kinetic energy, and temperature. So, in your summer assignment packet, you're going to want the notes packet. Now, you don't have to use the guided notes packet, this one. You don't have to use the guided notes packet. Feel free to use it though, because it'll tell you everything that I expect for you to learn. And you'll notice that there's this column on the side that says questions. That's for you to write down questions you have so you can ask me when you fill out your Google form after the video, so I can help you. So let's go. Now, hopefully you've already taken chemistry. If you have, you know that matter is made up of atoms, or maybe you know that even if you haven't taken chemistry, and that molecules are just a combination of atoms held together by chemical bonds. We have 3 states of matter. Well, there's really 4, but we don't study plasma. And you can see that their density and their amount of vibrational motion changes depending upon whether I'm a solid, which I'm really structured. I'm just kind of vibrating my molecules around. I'm a liquid, where I have a little more disorder going on, and gas, where I'm in constant random motion. We're going to talk first about gases. So let's talk about the 5 assumptions of the kinetic molecular theory, which applies to ideal gases. So what it says is that gas molecules are tiny, they're very far apart from each other, and because of that, they don't really exert forces on each other. They're in constant random motion, so it's not like they have a direction. They're just woo all over the place. When they collide with each other and with walls of their containers, they're making elastic collisions. Remember from physics 1, an elastic collision doesn't mean bouncy. It means that both energy and momentum are conserved. Of course, in a collision, momentum is always conserved, but in an elastic collision, energy is conserved. Like I said before, there are no attractive or repulsive forces. That's why we have these elastic collisions. And more importantly for this video, the average kinetic energy of the gas particle is dependent on the temperature of the gas. So let's talk more about this postulate of the kinetic molecular theory. So here is an equation. You'll find this on your equation sheet. It's the average kinetic energy of a gas molecule is 3/2 kb times T. T, temperature, has to be in Kelvin. Anytime we're working with gases, if you did chemistry and gas laws, you know your temperatures have to be in Kelvin. Kb is Boltzmann's constant. Again, this constant you can find on your sheet, your constant sheet when you get it, when you start class. But I would write it down for now. And now we say it's the average because gas molecules are in constant random motion, and so they have actually a variety of different speeds, which is something else we're going to talk about today. So let's talk a little more about Kelvin, right? We in the US work in Fahrenheit. In class, in science classes, you always measure temperatures in Celsius, but we have to measure stuff at at Kelvin. Whoa, I'm looking at what is 0. Notice from what is 0, 0 Kelvin is when kinetic energy is 0, right? So if T is 0 in our equation, our average kinetic energy formula equation, kinetic energy is 0. So at absolute 0, when the Kelvin temperature is 0, all molecular motion ceases. In Celsius, that would be -273 Celsius. So we always have to be in Kelvin because if we were at 0 Celsius, we would still have molecular motion. Now, let's talk about internal energy. Internal energy is all of the energy inside of our gas molecules. Really, it's inside of all of our substances, whether we're talking solid, liquid, or gas. It's symbolized by a U, which don't get confused with potential energy, right? We use U for potential energy like UG, or later this semester you'll see UE for electric potential energy. It's also called thermal energy. But it is all of the energy of the gas. So the kinetic energy, the motion of the molecules, and any potential energy stored in the bonds or associations between atoms or molecules. Now, because ideal gases don't exert forces on each other, this potential energy is considered zero. So the total internal energy or thermal energy of a gas is the average kinetic energy of all of the molecules. So make sure you write this equation down. It's a very important equation. So N is the number of molecules. So we just take that average kinetic energy formula and we multiply by the number of molecules. Now, if you've done chemistry, you know about moles. And we can relate moles to molecules. And we can actually relate moles and molecules through our two constants, Boltzmann's constant, and R, the gas constant, the 8.31, not the 0821. So we can also express this as N moles, 3/2 R, 8.31 T. So number of molecules times Boltzmann's constant is numerically equivalent to moles times the gas constant when it's 8.31. So just a little review in case you haven't had chemistry, or maybe you have, but you don't remember much. When we use a big N, we're talking about number of molecules or atoms. Little n stands for number of moles. In 1 mole, there's 6.02 times 10 to the 23rd molecules. Molar mass, which is also called AMU, atomic mass unit, is the number of grams in a mole. And in physics, remember from AP Physics 1, we use kilograms, so not grams, so we always have to do that sort of conversion. If we want to go directly from atomic mass units, which is molar mass, to kilograms, we just multiply the molar mass from the periodic table by 1.66 times 10 to the negative 27th. This is another constant that is, or equation, constant that's on your equation sheet. Let's talk about this equation, and this equation you should write down and highlight and star, because when we talk about the first law of thermodynamics, when you get to class, school starts, this equation is one you're going to mess up all the time. Anytime there's a change in temperature, right, there's going to be a change in the kinetic energy of the molecules, which means we get a change in the thermal or internal energy of our molecules or our gas. So delta U, that change in internal energy, is equal to the number of molecules times 3/2 times Kb times the change in temperature, or moles times R, 3/2 change in temperature. But this is not heat. It's not heat. We're going to talk about heat when you get into class, because heat you mess up in your brain all the time. This is the change in internal energy that's related to changes in temperature. All right, so we've talked about internal energy and how temperature is related to internal energy and kinetic energy, but remember, kinetic energy is also about speed. So let's talk some more about speed. So when molecules are moving in constant random motion, they're going to have a whole variety of speeds. As they collide with each other and collide with the walls, they're going to get a change in momentum. And so we can graphically, I love a graph, display the speed distribution by what's called the Maxwell-Boltzmann probability distribution. So this is an example of a Maxwell-Boltzmann distribution curve. Notice it's not a bell curve. So the average molecular speed is actually a little to the right of the peak for number of molecules, because it's kind of got a longer curve out here. So molecular speeds vary, and so let's talk about kinetic energy again, because remember, if all of these molecules are moving at all these different speeds, right, kinetic energy is 1/2 mv squared. So I have to deal with averages, right? And so the average of a sample's kinetic energy would be an average of all of the squared speeds, right? I would take this equation at any instant in time for all the molecules, and I would add them up, and I'd take an average to get that kinetic energy. But this is kind of cumbersome, right? I got to square all these velocities and then take an average. Well, isn't there a better way? Well, there is. If we take a square root of the average, this will actually give me the speed of a typical atom. So we actually have a name for this. This is called VRMS, or the root mean squared speed of a molecule. So the root mean squared speed of a molecule is just the square root of that average, and that would be the typical speed of an atom in the sample. So now if I'm talking about the average kinetic energy of an atom in the sample, I can use this equation. The kinetic energy average is 1/2 mass times the RMS speed squared of a molecule. Well, Okay, so now I've got kinetic energy and I have speed, and I had kinetic energy and temperature. So how can I relate temperature to the speed of a molecule? Well, we can do that by taking those two equations and putting them equal to each other, right? If K average is 1/2 m VRMS squared, and that's also equal to 3/2 kBT for one molecule, right? I can rearrange this equation for VRMS speed. And notice my 2's cancel out because they're on both sides in the denominator, and I'm left with 3 Boltzmann's constant temperature in Kelvin divided by the mass in kilograms. So what we see here is that the average speed, or the root mean squared speed of an atom in a sample, is directly proportional to the square root of temperature and inversely proportional to the square root of mass. So that means that bigger masses move slower. And in fact, if we look at the Maxwell speed distribution of different molecules, we can see here that this is oxygen. Oxygen is diatomic, right? So its molar mass is 32. Here is helium, which has a molar mass of 4. And here is hydrogen, right, which has a molar mass of 1. So notice how as that mass decreases, the average speed increases. So lighter molecules move faster. So I want to know the internal energy of all the molecules in 1 mole of hydrogen at 300 K. Pause the video and see if you can answer this question. Well, we use this equation. We can use it in this form with molecules and Boltzmann's constant, or of course you could use it with moles and R instead of N and Kb. If you do that, right, it's just a matter of plugging and chugging. If we use molecules, right, you have to remember that there are 6.02 times 10 to the 23rd molecules in a mole, and then we just plug numbers in, make sure you're working in Kelvin, which of course the problem's already in Kelvin, and you should have gotten 3,740 joules of kinetic energy in 1 mole of hydrogen. Let's calculate an RMS speed. So let's take a look at nitrogen. Nitrogen is a diatomic molecule, which means there's 2 when they're bound together, and the temperature is 100 degrees Celsius. Now remember, you have to work in kilograms. Pause the video and see if you can calculate the speed of a nitrogen molecule. All right, so one of the first things you need to do is get the mass of a nitrogen molecule into kilograms. So if we go to the periodic table, right, a nitrogen molecule, or N2, right, would be 14 times 2, which is 28. And that's the atomic mass of nitrogen. So if I use my conversion factor that converts straight from the atomic mass into kilograms, you should get 4.65 times 10 to the negative 26 kilograms, right? Molecules are light, so it makes sense that their kilogram mass is teeny tiny. Now I can plug that in to my RMS speed equation with temperature. Again, make sure you put temperature into Kelvin, so you need to add 273 to that 100 degrees Celsius. So now it's just a matter of plugging numbers in, and don't forget to take the square root. When you do that, you should have gotten 576 meters per second. Holy cow, that's fast! All right, see you in class. All right, now it's time to go below the video in Canvas, click on that Google form. You have to be logged into your Rockwood account. So if you're not, you're going to have to do that. And then you're going to fill out the Google form, and you're going to answer some questions that summarize the video. You're going to ask me any questions, which is why I wanted you to write down questions, in your little side, so that I can answer them for you. So we make sure that you understand the lesson. And then there's some other calculations you're going to do, and you'll see those calculations are also on the bottom of the notes packet. So do those. Make sure this is turned in by the Monday before school starts. Can't wait to meet you guys.